Day 135, Honors Physics, Capacitors. Second day of Corona quarantine. Once again, these are capacitors or electrical energy storage devices. Don't call them capacitors. They're capacitors. And capacitance is measured in farads. Now we're going to be practicing a couple of problems, well, one today and one tomorrow, and then other practice problems in the homework. Over here on the right, over here, are rules that you're going to have to keep in mind that you may or may not be familiar with. But there's two basic types of circuits, but in this particular circuit that I have, it's really not a complete circuit yet. There's no battery hooked up. There's just 6 capacitors hooked up in what's called a network. Some of these connections over here in this system are capacitors that are in series with one another. Other capacitors are in parallel with one another, and some are not directly in series or parallel. You have to do some simplifying of the circuit first. So we're going to go through this step by step, and one of the keys is going to be drawing diagrams, good diagrams, as you go along. A lot of points for diagrams in these. But I'll run through these rules that may or may not make a whole lot of sense as we begin, but I'll explain them as we go through. There's two types of circuits. There's the parallel type of circuit where you have 2 or 3 or 4 capacitors like side by side or in multiple pathways through the circuit. Series means there's one pathway with 2 things in a row or 3 or 4 things in a row. And here are the rules, the mathematical rules that then we apply to the equation that we've already had. I'll write it over here again, and that is C equals Q, I'm over here on the far right, over delta V. So we're using that equation that I just wrote down there in red. I'll circle it. We're using that quite often, but then apply these rules to the different parts of the circuit. Now going back over to the circuit, there's all these black lines represent wires, but like say down here, I'm drawing a red dot here down on the bottom. That might be called point A. It's just kind of random. And point B up here, that's where you'd connect your battery connections, points A and B. If you connect your battery at point, take a wire from the plus side of a battery to point, say B, or it doesn't really matter in this case for most capacitors, doesn't matter which way you hook them up. You'd hook up, say the positive part of the battery to point B and the negative part to point A. We're not going to get into the difference between those. What you're going to be getting into is simplifying these circuits and then figuring out how much charge is on any particular capacitor, because right now they're rated for their capacitance. Now, these take a lot of practice. One of the things that you need to do when you first see these diagrams is identify where the series and where the parallel parts are. One way to do that, and I'm going to be a little careful because the diagram can get messed up. Like, for example, you think of it this way as roads. If I'm at point A and I want to get to point B, how many different ways are there to get from point A to point B without backing up? For example, I can go to this spot right here. It's called a junction. That spot right there is called a junction where there's a bunch of wires connected. I can go here, up this way, over this way, and to point B. So by definition here, by watching this, if I go along this route right here, those two, the 3.5 and the 5.0 microfarad capacitors, are in series with each other. Because once I'm on that road, I hit one and the other without backing up, they're in a row, they're in a series. You could have 3 or 4 in series if you want, but those are in series. So together they're in parallel with, say, this pathway. This pathway goes from A to B, where I could bypass the other ones, but these two together over here are in parallel with this one, which are also in parallel with all of this stuff over here. Now let me go to the far right. Once again, if I can go this way, I can go from this spot right here, once again, a junction where 3 wires are, say, stuck together or connected together, those 3 black lines. If I go up this way to this spot right here, all right, then I continue on. Technically, and here's a tough one, this one, the 7.75 and the 1.5 are not in series because these two right here, the 0.75 and the 15, are in parallel. In other words, if I'm at this spot, I have 2 alternate pathways to get from that spot to this spot. So these two are in parallel with one another. So we'll practice that a little bit. But the bottom line is you have to identify where series and parallel are. The easiest part of this one is that these two are in series. Now the rule for series, if you have 2 capacitors in series, the rule for series, and here are the 3 rules for series for the 3 quantities we need to worry about. The potential difference, these are all delta V's, the charge on the capacitor, and the capacitance. EQ means equivalent or combined capacitance. That's what that EQ is right there. But in this particular case, if we start with the 3.5 and the 5.0, and I'm going to do a couple things. Well, I'll do that first. So I'm going to do the math there. The math is this. It's the equation, the 1 over total. So I'm going to do, basically I'm going to do this equation. I'll circle it over here on the far right. That's the equation I'm going to apply to the 5 and the 3.5. In other words, so I'll do it over here to the far right, because I'm going to need some space for my diagrams. So basically I'm going to have 1 over the C, I'm going to call it C total. They call it equivalent, equals 1 over the 5.0, that's 5.0 micro, I'm leaving off the units for now, plus 1 over 3.5 microfarads. Whoops, I didn't need to put the micro on there. It's micro. So let's do the math there. So I did the math, and the total capacitance, then if I combine all those to 2 sig figs, 2.1 microfarads. So I also mentioned a minute ago, okay, so I'm going to redraw this diagram here in a second, but these two are in series. They're equivalent capacitance. In other words, they're acting together as if they're this far right here. They're acting as if they're really a 2.1 microfarad capacitance. So it always turns out that if you have two in a row that are these values or any values, the combined value, combined capacitance is lower than either one of them. Mathematically, that's how it always works out. This number is always less than either one of the two numbers or three numbers if there's three of them in a row that you started with. Now, going back to the diagram, these two are in parallel. In parallel, the rule is a lot easier. In parallel, to find the equivalence of these two combined, I'm going to put them together as if they're acting as one. It's like, simplifying an equation. You're kind of combining like terms. You're going to combine these two. The simple is right here, up in the diagram here on the right. It's just simply adding those two numbers. 0.75 plus 15 is 15.75. So I'm going to go to 4 sig figs here right now. I'm being a little inconsistent. But the new diagram would be this. I'm going to draw this now. It's very important you draw this diagram. So I'm going to come down. Okay, here's point B. So what happens is this. You have this line across the top. So on the far left here, the 5.0 and the 3.5 have been combined to make 2.1. And I'm just going to leave the micro off right now. All of these are micro. 2.1. It's 2.1, that capacitor right there. The one in the middle is still there, the 8.0 is still there. And then on the far right here, so my lines, I'm not doing a very good job of drawing these things. Let me improve my diagram a little bit, maybe. My pen is not working too well. Okay. On the far left, let me erase this a little bit. Okay, on the far left, this is then the combined calculation we just did. That's 2.1 microfarads. In the middle, that's still the 8.0. I'm just going to say 8. It's 8.0. On the far right, I still have the 1.5. These are all micros. But the one on the bottom right over here, I've combined the 15 plus the 0.75. That's 15.75. I'm going to go to the middle and say, okay, it's 8.0 in the middle. So on the far bottom here, I have point A. So once again, you can think about this. There's three pathways to get from point A to point B now. So if I go from A to B, I can go over to the left and up to B. I can go from A straight up to B, and I can go this far right up to B. So those three segments there are all in parallel with each other. But over on the far right here, these two are in series. So I got to put those together first. Now in series, I have to do that equation again where I do 1 over 1.5. I'm going to go far over here to the right and do the calculation. So 1 over C total for the second time, I'll call this a 2, equals the 1 over the 1.5 plus 1 over 15.75. So the combined total for the second time, I could have called the first one number 1. I'll put a subscript up there, number 1, the first time we did it. Pause and get the answer. All right, if I do all that, to 2 sig figs, it comes up to be 1.4 microfarads. All right, so I'm going to draw my new diagram here. I'm going to just circle some of these things to kind of keep them organized. So my first answer of combined was C sub T1, combining those two. Second time, I'll put the units on here, it's microfarads. So there we go. And I'm going to redraw my diagram. Once again, the key is drawing these diagrams. So my new diagram is starting to simplify now. I'm going to run out of space, but Okay, I'm going to start with point A at the bottom. That's point A. And I have, basically, I still have the 2.1 on the far left. Okay, then I have, this is, and point B. Okay. So I have point A at the at the bottom, point B at the top. I have the 2.1 microfarads capacitor far left. In the middle, I still have the 8.0. On the far right now, I've got a 1.4. Those are all microfarads. But those are all parallel. There's 3 pathways to get from A to B. All right, those are all in parallel. So the simple rule now is just to add them up arithmetically. So I just take 8 plus 2 plus 1. So that's 11.5. So put them all together now. My final diagram, which I would do on the lower page, but I'll go on to another page. So I'm just going to remember that's 8 plus 2, 11.5. I'm going to draw my final diagram. My final diagram is I have an equivalence capacitance of 11.5 microfarad, combined capacitance of those 6 capacitors, point A and B. So that's my final answer for the reduction or simplification. And other questions that you're going to get to in the next page is they're going to say, okay, now what if we connect a battery to point A and B? I'm just doing a little extra extension here. So if I put a battery now, which is symbolized like this, from A to B, I have a simple circuit. And I say I put it like a 20-volt battery. Just like the previous problem now, it might say, okay, calculate the charge on there, where you got to plug into C equals Q over V to figure out the charge on that capacitor. And once you do that, just a foretaste of things to come here, well, if you do that, you get C equals 11.5, that's 11.5, divided by 20. So, whoops, let me back that up. C is what I know there. I know C, not Q. C is 11.5. 11.5 microfarads equals, I'm looking for Q, the charge on there, over V, which is 20. So I'm going to put the 20 in there. So Q comes out to be, 23, 230. 230 microcoulombs, if you cross multiply there. And that would be the amount of charge on that capacitor, which is not a real capacitor. It would be the capacitor that's the equivalent of all those 6. Then you can figure out the energy stored like we just did in problem number 1.